you can actually click and import GitHub into Colab, and it'll give you a list of all the notebooks that are on that GitHub.
I forgot to say that if you have any technical issue, you can ask me and I will go and help. Okay. Good.
So there's a bunch of different notebooks under this repository, and they basically go through this this Iris Dataset, which is essentially characteristics of different kinds of flowers. It's a pretty small data set, and it might actually be too easy, so we can actually go to some other ones if you want. What I would suggest is to go through them in this order. So it kind of goes from very, very simple to more and more and more complex. At the start, it's just visualizing the data, and then it's training just a simple scikit-learn model in as few lines of code as I can do. And then as we go, it starts to do things like cross-validating the model, finding the optimal hyperparameters, and finally the last one is a kind of like over-engineered, fully automatic. Put a data set in, and it'll tell you the best model, the best parameters. It'll show you the cross-validation and how it compares with the actual tested error and with that correlation. So it's overkill, but as an example of how you could completely automate this entire pipeline so that you could literally take a new data set as a CSV file, hit, machine learn, and get your answer out, just so you can see what it would look like. So I don't know I guess we'll go around and see how people are doing.
So,
Step by step. I don't know if I should just walk through the code.
which notebook do you want to start with?
I think people should start with this visualized data. And this is that notebook.
So, could everyone access Colab and import the GitHub thing? Okay.
Yeah, I think this is basically if this doesn't work, then we need to get that fixed before we can do anything else.
Yeah, so please check that you're actually accessing.
This is visualized data. And literally, this just loads the Iris data set and then plots it in a feature by feature.
So I think everyone is fine.
Okay. Yeah. You have to actually do something so that you can edit it and save it. You can edit it, but it won't save it.
Oh, okay. I just want to run it. I'm not changing it.
Yeah, that's right. So it should say there's an icon here, this thing at the top, and it says it's in playground mode. So that basically means it doesn't have an identity on your drive yet. So anything you do is going to get deleted when you close your window, but it's not going to upload it to GitHub and erase everyone else's copy. And if you want to save it to Drive, I think you can actually just save a copy in Drive and then open that up. And then you should be able to actually save your edits.
Could you tell us again how we open this?
So you need to go to.
Anaconda a lot, but I've never used it before.
So you need to look up Colab on Google and click on the link.
Yeah, I opened Colab.
And then I sent everyone a GitHub link.
I have the GitHub.
Actually, lots of people thanks to like that.
Okay.
I don't know.
Or is it just like, so how do you do this?
Oh, I didn't even see that.
I don't know.
You have to basically open a notebook. No, I just pulled the Yeah, I don't know. These things like this. So,
What are the colors of the
I just mentioned
yeah.
Is anyone else need help? Yeah?
Still got some time.
This is GitHub. This is just a lot of files that are stored somewhere. This is Collab. You can actually run code. Like this. Are you okay?
Yeah. The next step, go to the simple example one. So basically, this is going through that. So the downloaders actually still on. So this is just showing you how to load data from one of the scikit-learn data sets. They basically have that data set.
Yeah.
So in that data set, it's an array. If you want to visualize Iris Dataset, just open a new insert.
So I think you can run it in this environment, but if you want to save it in your own drive, you just want to find it and then save it in your drive. Save copy in your drive. And this should be now in your drive, and you can just run it there. Yeah.
I didn't see anything.
So this is just importing libraries. So you have nothing.
Okay. So we're just looking. This is
This when you click on it's actually right. But there's one. And then if you click here, then I click, I don't know. Now we have to run it.
okay.
So you can run it actually, but I think he will explain what you're supposed to say. And then you can just go down.
I'll show you.
Okay, thank you.
All that stuff. And then this is just pulling things out of that.
I'm just reading all the data.
Because I think you could do it publicly.
Okay, but
Is it?
it's really basic Python stuff. Maybe can you help?
Yeah,
And then
I'm.
we'll
I'm
okay, yeah.
further than him.
Okay, but where are people? Right? Is visualized data okay, or are still people working on visualized data?
What do you mean? Because you didn't explain anything about this.
Yeah, I mean, basically, I'm not sure what I should explain about this.
I think you should just describe what each cell does.
Okay.
Could you explain how this modifies how this works? Because I understand what the code is doing, but I have no idea how this operates.
So just if you hit Shift Enter, it runs the code in that cell, and it'll just run each cell as you do it. So you can run
How
And so basically, the top bit here imports libraries, and from scikit-learn, we're going to pull the Iris data. That there's a where is it? Yeah. So scikit-learn has this datasets module, and it has a whole bunch of different datasets that are just built into scikit-learn. So you can replace load Iris with pretty much any of these. This, classification or regression, and it'll give you some inputs and some labels or some numbers to predict. And it basically gives you this data structure. So for example, if I do load Iris and then print what I got. So I have data and it's the actual inputs. And then I have targets, which is the labels. And then I have the target names and the label names and things like that.
I'm not sure if people know what is the Iris dataset. They don't.
Yeah, so that's, if I just go back to what it was.
I think they don't.
So
If
what's
you
the
don't tell, they don't
background
know
for
what
this
is
data?
It
Iris.
doesn't matter.
Oh.
That's kind of my point. It doesn't really matter where this is from. I mean, yes, so we can talk about what it is, but from the point of view of the machine learning, it's literally a table and labels. And that's the kind of mindset that I want you to have. This is just inputs and outputs. And you could put anything here. You could replace irises with wine or Boston
But
retail prices.
It's possible that people don't even know what is an Iris. I think you have to explain.
Are you sure?
I mean, not everyone is an English speaker.
Because the output we don't understand what the output mean. The background of this.
Okay. Yeah. Yeah, I'm trying to figure out how to explain what I'm trying to get at here. I really want to try to convey, like, all of this process doesn't matter what the data is. So it could be flowers, but Iris could be kinds of car. And at the end of the day, for this entire procedure, you don't need to know that or care.
But I mean, you haven't even said if it's a sequence. If it's like, people have no idea what this is.
It's the tabulated data.
Yeah, it's tabulated data. And this first thing, what it's plotting is basically taking every feature of that table, and it's plotting one feature versus another feature. So you can kind of see, okay, why the features are all, of course,
So
directly
it's just a
correlated with
simple
themselves.
demonstration of how we explore the
Yeah.
relation
Yeah.
between different parameters.
Yeah. Yeah. So for example, if you look at this and you look at these patterns, you can see that probably the red class is going to be really easily classified because it's essentially completely separated from everything else. So if you just took even two of these features and drew a plane, you could perfectly classify the red class, right? But the what ended up here as being gray and orange, they overlap in all of the two-dimensional plots. Although there are some that they're very, sorry, I'm pointing with my finger. There's some that they're very close. So probably, in these axes, for example, the classifier might put a decision boundary to say, okay, this is a good way to separate. But actually, if it used more than two, it might be able to do it perfectly. And this is kind of the, the structure of this data set. If we go to a different data set, for example, I can do wine. There's a wine data set, which is, I guess, about the quality of wine. And this one has 13 features, right? So this is going to be a bit more complicated. But it's basically the same thing. If it's a table, it's just X's and Y's. It takes a while because it's now big. Yeah. So in this data set, it doesn't look like it would be quite so easy to separate them, right? I mean, of course, it's plotted a little bit harder to see, but there are a couple here. Maybe this combination of features here would be good or something like that. And the disadvantage is if I have to do this by hand, it's really hard for me to imagine, say, 3 features co-distributed or 5 features co-distributed. But for the machine learning algorithm, it'll just pick it out, assuming there's data to support it. So if you want to use the Iris dataset or use the wine dataset or use, there's I think a couple other ones, so here, this page, this scikit-learn stable datasets. I don't know, maybe I can zoom this in. So that has the details of the dataset if you want to look into it, and gives a list of other datasets you can look at. I would suggest that you can use any of these if you want, but it should be a classification dataset.
Maybe I'll share a Google Drive document with links in it, and you can.
Okay, sure. Yeah. So I guess what I would suggest is, if you're at least comfortable with like getting Colab to work and getting these things, maybe to move on to the simple example.
So when you switch to the wine data,
Yeah.
you already pre-archived all these like data sets from the site base?
Yeah, they're built into the library.
It's built into the library. Yeah. And do we also have access to that?
Yeah, in Colab. So that's the nice thing, we're all using the same environment, so everything should work.
Can you show again the list of no the
URL?
yeah. I'm just going to. I will share it with you. So I'm sending it to you by email.
To me.
So you can paste all the links that you want in the shared document.
Ah, okay. Sure.
Nicholas,
Yeah.
so these database, these data sets are used for our learning only, right? Not the real data.
Oh, it's
I mean,
real
they are
data.
Real data,
Yes.
but then for your learning. But yeah. I mean, we could have made completely artificial data as well.
But this is from the world.
Yeah. But it's really, the intent is to get an idea of what the workflow is, so that if you had different data, you wouldn't have to scrap everything and then rebuild it for your own thing, but you could actually just substitute a CSV file of your own or something like that and have it still work. Okay.
Did you receive the?
I don't think I can edit it.
Can you reload? Okay.
All right, I guess I'm going to do this with a show of hands because I'm having trouble keeping track of where different people are.
Yeah.
So how many people want to still go into more detail about the visualized data notebook? And how many? Yeah, so show of hands for that. None. Okay, good. So simple example. Okay, none. Okay, one. Okay. All right. So again, the start is the same, right? I'm just maybe if I do this, it'll be easier to read. If I'm just loading libraries that I'm going to use. So NumPy is a general array processing library. Matplotlib is for plotting, and then the dataset loader. And the only new thing is I have this SVC thing, and this is a support vector machine classifier. So instead of SVC, if you wanted to, you could say use logistic regression, right? Or logistic, yeah, it's logistic regression. I typed something weird. Right, and then that is just another machine learning algorithm that has been kind of boxed in a standard way by scikit-learn. So again, we're loading the data, but now the difference is there's a train test split. So I'm just going to take the first 100 points as the training set and the last 50 points as the test set. And there would be a problem if I did that as the data came, because if you saw in the previous one, well, actually this one doesn't have it, but you can kind of see here. Look at this target row. 0, 0, 0, 0, 0, 0, 0, 0, 0, etc. 1, 1, 1, 1, 1, 1, 1. So the way this data set is presented to you, all of the labels are in order. And if I take the first 100 points as a training set and the last 50 points as a test set, I'm going to have a training set that doesn't have any 2s and a test set that has nothing but 2s. So first, I'm going to shuffle it. And here I'm just doing it by hand. Well, by hand, using NumPy. But the scikit-learn stuff also has stuff that will do shuffling for you. And I'm just reordering both the x's and the y's according to some random permutation. Now, let's say I were doing this for a publication. Well, if I didn't fix the random seed, every time I run this experiment, I get a different train test split. And so my results wouldn't be reproducible. So it's good practice to initialize the random seed to something specific when making your train test splits, or otherwise keep record of how you split the data so that you can actually reconstruct this later on. But, okay, so let's go ahead and load. And then this is literally it. This is machine learning here. You're done. This is probably one line too many. Actually, we could probably do this with one fewer line. So I'm initializing this SPC model, and then I'm going to fit it. And my X inputs and my Y inputs are just the arguments of the function from the training set. Predict on the test set, and then print out the accuracy. And that's it. Done. 98% accuracy, you can go home. On the Iris Dataset at least. If I, instead of doing this, I did logistic regression, I don't have to change anything else, I just change the name of that function. Okay, maybe I do have to change something else. Why did that not work? Is it, but there's no accuracy.
It's at the top.
0.92.
It's just the future warning.
Okay. Yes, okay, so it did work. Yeah, so logistic regression doesn't do quite as well as the SVC. I guess that's not too surprising because logistic regression is linear and SVC is nonlinear. So that section that we saw in the visualization where those two clouds are overlapping all of the one variable by one variable, the SVC can kind of draw a curve to cut them, and the logistic regression can only draw a line.
So if this accuracy is very low, let's say 0.6, does it mean we shouldn't proceed to the next step, whether we should modify something?
Well, generally what you're going to want to do is have an idea of where all of the different things you have available are. So let's say I just did it with logistic regression, and all I know is 0.92. Then it's hard to answer that question. But if I've done logistic regression and SVC and a couple other methods, and then let's say I saw let's say that's 1 and that's 1/3 or whatever chance level is for this. If I see something like this, where all my different methods are kind of clustered together in accuracy, then maybe that's as good as it's going to get. And that could be telling me this is just a really hard problem. But I might see something like, this will be a lot more common. So I want to try a lot of different things so I can tell whether I'm in this kind of situation or in the other situation.
So the higher value, the better.
Yeah, generally the higher value, the better. But I also want to know, like, is everything doing about the same? So if everything's doing about the same, maybe I'm not going to get much better. Like if every method is giving me the same error, that could be telling me something fundamental about the data. Whereas if a couple of methods are doing really badly and the rest are doing well, or maybe even 1 or 2 methods are doing really well and the rest badly, that suggests there's still some kind of structure and there's a structural difference that some of the methods are picking up on and other methods are missing. And so that means I might have some hope. You know, if I saw this, I might even think I could get that because there is some difference that matters. But if I didn't see these points here, I'd be a little bit more suspicious that this might actually be the real range of performance that you can get on this data set. You can also inspect the classifications in detail. So like in this case, we've got these predictions. 0.92 is pretty good because there's enough errors there to be interesting, right? So I have my predictions and I've got my actual labels. So I can see between these arrays, I have a 2 misclassified as a 1, or I have a 1 misclassified as a 2, and things like that. And then what I can do is I can make a table. I don't know if there's an automated way to do this in scikit-learn, but I can do this. I can say confusion. And I can say confusion. What I'm doing here is I'm going to show how these things got misclassified. Sorry, I should have a color bar there. Oh wait, no, that's weird. Test y, not y. Makes more sense. Okay, yeah. So you can see it's almost, the diagonal is pretty bright, so it's getting most everything right. It's 92% accurate, so that's not too surprising. But most of the confusion is between the second and third class. And if we go back to the visualization, the old visualization that has the actual Iris data.
I think it's still running on the wine now.
Yeah, it's one.
Yeah, something weird. No, it's connecting.
Data.
Yeah, this is the wine data. I'll let that go in the background and maybe it'll fix. But basically, if you remember, there are those 2 clumps that were overlapping, so this kind of makes sense. And then, you know, you could do other things, like you could actually plot, for example, let's say we looked at the actual data and how it got classified. Right, so this is showing the classifications that the machine learning algorithm output, and we could compare this, plot this side by side with the actual ones. Okay, so for the most part, it's actually quite an agreement. and the points that are causing a problem seem to be something down here. Right? This might or might not be a useful thing to do in a given case, because if you have 1,600 features, then you're not going to just pick the ones that are going to tell you what's going on. But you can kind of spot inspect things to try to get an idea if something is really, if something is not working. But if it's working really, really well, you might not get that much extra information by doing this kind of thing. This is more like if it completely failed. I wonder if I can make it fail. What's the worst model?
What kind of question is? What is the worst one? Nothing fails on Iris.
Yeah, I know.
Even
So that makes
Cam
it an interesting challenge, right? I think naive Bayes is fine.
Yeah.
I think rich regression might be pretty bad. Rich classifier, try that. Probably terrible. K-nearest neighbor, no, that works on those, doesn't it?
Yeah, it does.
%84%.
Ooh.
That's pretty bad. Okay, there. Now I'm happy. Okay, so again, it's these two classes that are giving me trouble. This is doing worse than a linear model, which is kind of impressive. And what does it get wrong? It really, really sharply just wants to have a decision boundary that cuts off the bottom set of this prediction into class 1, whereas class 2 has some overlap. It says, I only want, I think ridge regression, is it one of the ones that it goes sparse, so it tries to only use 1 or 2 features? Well, we can use the documentation for that. Ridge classifier. Ridge regression. Let's try that. Oh, it's L2. Okay, so it just over-regularized. Yeah, so it basically really, really wants to avoid overfitting, so it doesn't allow it to have any kind of complicated dependency between multiple variables. It's really trying to force as many of those constants to have zero dependency as possible. And so it's basically missing information that exists in the data. It's underfitting. 0 and 1. I don't know. Something about flowers.
So you just picked one of those at one.
Yeah, we can do another one.
Oh, I see. Oh, yeah.
Yeah. There. That's another axis. Yeah, I'm trying to be as cavalier as possible about what this actually is. Yeah. Okay. Yeah.
Can we improve the accuracy by changing the terms of iteration?
Not for a lot of these. Most of these don't actually have a learning rate. They directly solve a linear system, and then the solution is the solution. But we can mess with hyperparameters. Actually, yeah. Why don't I jump to that? So if you want to see what kind of thing you can do to improve the performance, open up the hyperparameter search notebook. And here, what I'm going to do is it's the same as before. I load the data set, same thing. But now what I'm going to do is I'm going to have this C parameter in the SVC change. And this particular parameter, again, I would say look at the scikit-learn documentation and tell you about it. But it happens that this one, you should vary it between like 10 to the minus 5 and 10 to the 5. That's the kind of natural range of it. And they should have some example of the C parameter somewhere here. Except this got a bit bigger since the last time I looked at it. Now it's very. don't actually show the grid search one. There was a grid search example for this. Oh wait, no, maybe there it is. That's the RDF. This. Yeah, okay. So you can kind of see when they look, all right, when they show the accuracy of this on this data set, these things vary by orders and orders and orders of magnitude. So for this one, you want a wide range. So we're going to do e to the minus 5 to e to the 5, let's say. And I'm putting that into this array here. And then I'm just going to train a classifier on every single value in my array. And I've got essentially a bunch of different train test splits using this stratified shuffle split thing. So I'm going to do 10 splits and average over them. And then I see that my accuracy has this kind of behavior. Right? So it's pretty noisy, right? I can kind of see by the overall structure that there's probably a peak around 10, like 8 times 10 minus 1 or something like that. Not pretty close to the default value, actually. And if I go very far to either end, the accuracy decays a little bit. But Iris is actually quite easy, so it's hard to improve the performance of this very much. This is not the clearest way to see the improvement, though, because the accuracy, I either get a point right or wrong, and I only have 50 points in my test set. Or even in this, I have 15 points in every cross-validation test set split. So I'm going to have this big quantization effect on the noise. What I can do instead is I can have the classifier predict the probability and then use that log loss that I introduced at the beginning. And if I do that, I see this kind of curve. Here, low is good, right? Small log loss is good. And here it's actually saying that the optimal value of the parameter is pretty much between 10 to the minus 1 and 1. It's got a fairly wide basin where it's going to perform decently well.
So Nicholas, can you remind us again what's the purpose to do this and what's the problem?
So let's say in this case it's a really easy data set and we're very close to the best parameters just by default. But let's say we weren't. So let's say this data set were hard or we didn't know where the right parameters were. So our defaults were somewhere out here at 10 to the minus 2. Then our log loss would be really high, right? This is basically chance level performance. Even though the accuracy is quite high, the confidence in the probabilities is completely wrong. So it's really overestimating uncertainty about points and things like that. So if we were here, we would say, okay, well, we have a bunch of different models, and we want to try to improve things. We want a better accuracy or better log loss, or whatever. How do we go about that? If we're here, and we need to be here, and we're using this kind of model space, there are a number of parameters that tell the model how to weight between overfitting and underfitting. My data looked like this, and it was fitting this. I'm underfitting. If it's fitting this, going through every point, I'm overfitting. And that might explain why I'm not getting the best performance. So what I want to do is I want to just automate the search to find the best values of those parameters so that I can try to maximize the performance of the model.
And the parameters you are searching is not present in the previous database.
It's not in the database, it's in the model.
The model.
So SVC has two major hyperparameters called C and gamma. And basically what these do is they say gamma is sort of like a scale. So if the data, what's a good example? So let's say the data look like that. Then if gamma is very one directional, I think very small, it's using big blurry functions to model this. So it put the entire thing in one big blurry blob. If gamma is very, very large, it'll just draw a tiny circle around that dot. So it's the spatial scale of the decision boundary. And then C basically says, okay, if I have my decision boundary made of these little regions of a certain scale, how many of those regions do I get to specify? I want to penalize the model for using a lot of regions to explain the data, and if you use very few regions, it's better. Well, if C is one way, and if C is the other way, it says, I don't care, use as many regions as you want. So as I vary C, I'm going to vary how constrained and forcing the model to be in trying to fit this data. And like this explanation is something that you can understand about individual algorithms. But at the end of the day, to this pipeline, it's just a number that's being optimized by the pipeline. So the point of this kind of workflow is that you actually stop, you don't have to actually know this, or you don't have to look at the data and say, what is the characteristic scale of my data? Because, you know, in 4-dimensional data, you can do it. But if we had 4,000 dimensional data, where every axis had a different characteristic scale and things like that, it would be really, really hard for a human to look at that data and make a good choice. So we want to have somebody to check our choices and then find our choices automatically. That's kind of the idea. Does that make sense? So what was next? Okay, so for this SVC thing, if I want to get probabilities instead of classification boundaries, I can add this probability equals true flag, and then instead of predict, I predict problem. So the result is going to be very similar as before. I get my accuracy, it's 96%. But now each of these points, rather than being a sharp 1, 2, or 3, it has a probability of 1, 2, and 3. So I don't know if it's really visible in here, but because again, the Iris Dataset's a bit too easy, but some of these points are halfway between green and blue. So that's showing the sort of, these points, it will actually say, I'm not actually sure if it should be green or should be blue. It will actually give you a more nuanced read. And I think that's a useful thing to be able to do. So I guess what I would suggest is, just to make sure that you're comfortable with this workflow, try a couple different classifiers from the scikit-learn documentation. You know, you can use I'd recommend maybe looking at this random forest classifier, for example, and try to see how that works on the data set. Make sure that you know how to just switch things out. If you want the list of all of these things, there is on the main page, there's this classification category, and you can basically take your pick of any of this, up until this point, up until 11, I think. And you can see how this works. And hopefully it should be really smooth to just switch out one model to another. And that's kind of what I'd like you to get from the simple example, at least. I don't know if should I move on, Hans? Or okay, I don't know. Okay, sure. What happens if you just run that function with x equals fetch parallel California housing? So just say like data equals. Okay, so you need to import that first. So it should be and what doesn't matter what you call it, whatever you want to call it. And then parentheses. We also so we go back to the top. See where we import load items, right? So we put commas. But what do after load items? Shoot. And then put fetch
somewhere, and you want to
and then go back down to where you're saying cat equals.
And
This is the language.
this is
Yeah, I
not the
think so.
language, this is of mathematical expression,
At the bottom.
an array.
Okay, so mathematical tools.
There. You just
It's
hit the
just
code
one big file with some code. And this one is also library, but for plotting. So
Ah,
for making
okay.
that.
Okay, so this contains tasks that we do.
And this is library with data sets. So from here, we can also this
Yeah, and then
wine.
In your case, we will go to first build
Yes,
construct
in Ruby. Yes.
What does it mean when C is like less
These
than?
are the
Let's say C is 0.1.
it's just a number that scales the cost of this, of having very large coefficients. So when C is very, very small, the cost is very large to have the coefficients be non-zero. If C is very, very large, the cost is very small for the coefficients to be non-zero. So it's like, yeah, if you're doing like linear regression or something on very high dimensional space, if you make C extremely small, most of the entries are going to try to be very small. If C is very large, then you do. And that kind of forces the model to prefer smooth solutions over very complicated solutions.
With that function, what's it called? Cross entropy.
Yeah.
It's trying to figure out what are the right.
Yeah. Yeah, it's basically saying since you have this training validation test split, you can use that validation set to say, is this C value good? Is the C value bad? And then you find the optimal one and you try it on the test set. And that prevents you from having to guess correctly. Which these are only like maybe 2 or 3 hyperparameters for these kinds of models. But if we get into neural networks, you might have 1,000 hyperparameters or something. So that you don't have to guess.
And now you take the first 100.
Well, that's maybe 1,000's exaggerating. Some people do things that have 1,000, but like you're still talking 50. Maybe 50
No,
numbers
it's
to
it
describe
shows
them. So
100 randomly because it's 150.
What
The other question I have is what happens if you
choose 150.
so if you
If you
do
hold
K,
it as it is,
Yeah.
you don't have to.
what happens? So in this case, your space model splits
So the
data into
difference
three
is
classes,
between
labels.
Yeah.
But what if
train,
you throw in
test, and
like
validation.
5?
So you don't want
They
validation.
try to split these
Same.
5. That
Ah,
would be
okay, so the
Well, K-means is not
Validation.
classified, and K-means is a clustering algorithm, so it's a different type of algorithm.
So
But if you use
that's
K nearest
what's
neighbor,
here, there is no
then
validation.
it doesn't matter how many classes. It'll just say what's the class of the nearest point, and then it'll say that's what it should be. So like we can do K nearest neighbor.
Yes.
I didn't actually put that into the algorithm, but I should have done.
This is the actual training.
We do neighbors. K neighbors classified.
Here you predicted the binary way, so you would say to the point, is this point part of class A? Yes or no? Here, it's not.
96%.
I'm
So
70%.
everything works on this,
A
except for
could be
recognition.
30%.
Okay, but most of them are the outcome from this.
Yes, yes, the same data set and the
Sorry.
yes, you can choose which one is better for you. So that's what.
Yeah, yeah, so you like the reality just like test something out, right?
Just like 5 lines and then you can solve
And
it.
it's like
No, because
just see like
So this is the result.
Yeah, so I don't want to switch out the algorithms, I'm just
In reality,
the algorithm here, right? SVM, SVC.
So
And this is your algorithm. So when you make your predictions,
Because here you have a mix with
Yeah.
Predict labels. Search. So when you search like for predict labels, they are the ones that
Yeah, it's just I have to do it 10 times. I always do it.
is it the same notebook? So this is the hyperparameter search notebook. So this is basically doing for searching a lot of hyperparameters. If you want to test out algorithms, you open this simple example.
here is
And here you import your output. And then if you search for different tables, maybe you just
I mean, you ask
so here you actually
does it
fitting
belong to
your algorithm, fitting your model to your data, and here you do your prediction. So if you want to change the SVM and try out live days or random forest, you have to first import these algorithms. So you go back up to the libraries. And then you do from, you just add,
Here, you didn't.
just add a line. And then you do from SQL.
So we don't pay tax.
That's not how it works. No, you pay tax. So if you live in Japan, you have to pay tax.
If you're a Japan tourist, some of the electronics are tax free.
Gives you
But you're not a tourist, are you?
options.
No, I mean, we are, because we're visitors, we're like researchers, students, so we don't have that permanent visa card yet. So technically, we qualify for like tax-free code shop.
It
Because
gives,
our passports are.
yeah, so it gives you a lot of stuff, right? It
My
gives
passport
you,
is not Japanese.
You have to pay tax.
Yeah, you live in Japan, you have to pay taxes.
So
Like
maybe you
on
can
these,
choose
like,
nice
so yesterday I got earphones, right?
Mhm.
And if
import.
you buy one, it was like
And then maybe we
$40.
need to check
And
out
you
the
don't pay,
documentation.
it's like $40 or $50, you don't pay tax on that. So
You
you save.
I mean, you can try not to pay taxes, but I think you're supposed to.
can, what is this? Bayesian regression. So maybe you can look for, if you go SQ merge, space,
Yes.
this should lead you to exactly to this documentation. So here you have the whole 9 base class and regression 9 base. So basically what you can do is here from sklearn of 9 base, import Gaussian 9 base. So you just copy this algorithm.
Copy paste this
You can see
into here.
However, when you can delete a tab, you
You
can just
can change
initialize the
once you're
classifier.
completed
So that this line, this top line,
the
makes
interesting
it
because you have already written.
well, no, this
Exactly.
external line.
And then you execute.
That creates a.
So now you have imported your algorithm class,
You don't want
right? And now you can just exchange basically the algorithm
But you do want
by
the line. And then those are the two.
maybe just copy paste the algorithm.
Yeah.
Well, yeah, it's just not just the word, this is just a class. Copy paste, and then you can easily switch out.
And then.
You can instead of here use the SVC, which is the support sheet. You can just delete this and import exactly and then run.
Okay.
Oh, okay. So you just delete the in between because these are parameters that are difficult for the support vector machine. C parameter and the gamma parameter, just delete them and open and close parameters.
No.
So this would be like the default outcome. So if you run this, it gives you a test accuracy of 94, it's running the Gaussian 9 base algorithm. Now, if you want to inspect what kind of parameters this algorithm have, you just go into the package,
Yeah, it's simple, right? It's not
and then you hit tab,
such a big.
and this gives you the documentation of the algorithm. So here you can see, for example, okay, these are the parameters for the algorithm. So they have some priors, they have some variable smooth things, they have some attributes. So this is like a little bit more advanced, but this would equal like what you're seeing with C parameter and gamma parameter. So every algorithm has different properties and different kinds of.
Yes, tomorrow we'll use
But generally, like the default algorithms, it's very easy to switch algorithms.
There's also.
And there are several ways to do
Which
that.
is yeah.
Changed all the irises to matching. Is that what you're saying?
Yeah, you can.
Then it doesn't come up with.
It doesn't.
I think tomorrow there is. Okay, I don't remember. I think there's something.
Joining the Iris Dataset. Okay, I have to take a look.
Because I just literally changed all the irises.
So, okay, well, is it the same?
It depends who you are.
Does
If
it
you're
have the same
just
properties?
if you're somebody from Google, it's not expensive.
Yeah. It has the same properties. So data
Because
The best is to buy a computer that has a CPU, like his computer, or
but it doesn't show you.
mine is not a laptop, it's an actual
Have you
computer.
tried to
And
untype?
it's quite expensive, but for compared to buying research machines, it's not.
And that's
It's not the same price as
what constitutes a high accuracy.
I know some research related to
You want to go to school. You might say, I really don't want to do this. I really want to have my
evolutionary animals.
I don't know how the line is.
The geological times.
Yeah.
So they have
or you could do
A lot more.
Association. And they have
that's something
increased
but what
structure,
you're saying, her
the balance state of the elements and
elements.
location. Also they and also the date time. So
Yeah, the mean squared error is going to tell you like an error bar.
But,
is the same.
yeah,
It does assume that the algorithm is low stress and if it works, you'd have to do something more complicated. Or if you thought that assumption.
It's not adding first step, next step.
Yeah, this is interpretation of the base. It's how we were back.
Okay, so,
but there is a.
so, well, at least we can
No,
go to the point, so like,
really accuracy.
Yeah.
I don't know if you saw the slide of Suzana,
So,
she showed different image datasets.
wrote this here.
One had
Yeah,
14
maybe
million.
This, and I want to draw the data.
Then another thing, then the trade-off between the, you can have a lot of data, you can have a lot of time. You can train with it for a week or a month, unless you can probably buy a big machine.
Oh, well, you didn't rerun the prediction, so that's a problem. So you need to also have a line that says like predict pop-up. So you're probably actually going to be all right. Yeah, you need P equals C left dot predict.
That's not a lot.
Okay.
That's very small. And compared to 14 million, it's really small.
I don't know what your train test split is. Sorry.
It's also not.
And
And
that's
then
really
down
good.
here, you need some
That's
more
why
time
you want
to
to
predict. I think you can work that one.
Glad to hear it.
To manage all these data. I feel like I'm trying to use words randomly. But I think I have not really. I would like to.
Okay, you can use the plot list. Yeah. It's HIS. And then you can do parentheses and then the data. Whatever it's called, you put in Iris Dataset. I need Iris Dataset. Well, whatever variables you said Iris Dataset. No. You go on. We'll go to log she sells. No, it's just where you load the house data. So you say data underscore iris equals this. That's putting it inside data underscore iris. Okay. When you do this, you're saying I want the contents of data underscore iris. So you want to write, and then, but you, that shouldn't be in the quotes. Oh, yeah. No, it's in parentheses, but not quotes. No, you want the parentheses, you don't want the quotes, the apostrophes.
I think so. I think we almost solved this, but
Because data is several different things.
oh, it's right here.
What do you want to plug in Instagram?
I think we got it.
Do you want the targets? You want to know the Instagram? So then, put square brackets. And you give the after data. And now I can sequence. And then there's going to be a login. So you're talking no, that's fine. Between the square bracket and the parentheses.
Practices on training for specific types of data. Do you have some example?
You mean about this specific data set?
Yes, like sequence data.
Sequence data with this, you won't get anything.
Oh, there's no such data.
And I mean, you can find some sequence data in this, but with Nicholas' code, you won't get anything because it's a completely different type of data.
Oh, so the method here is not applicable.
No, this is only for classification.
Oh, I see. Okay. So usually for sequence data.
I know, it will show this one.
So-
All this is one.
And if you remember Nicholas' slide about why sequence data is different from table data. Sometimes you can put the length of the sequence like here. It's very easy. Every flower has maybe 3 characteristics and that's true for all of us. But if your sequence, the size will be different, the index can be important, but sometimes it's not important. So you cannot use this kind of sequence data. But tomorrow, I think I should check with Suzana, but typically in sequences you
Well, I mean,
can have text
if you want to know
audio
what it looks like.
or videos. These are sequences. And what you can do. Common tasks are try to predict the next sequence or try to classify the sequence.
Classical.
Yeah.
You could,
Or
or you
how to say, find some
okay, we'll try
yeah
it.
inside sequences.
Because now the technology is to predict the structure of the
Yeah.
from the sequence data, which is very difficult. But still, we can try to find the highly conservative and then try to see which residues are critical for maintaining the structure of the active center, which I think is also very interesting to see. Yeah, I haven't. So I haven't had a very concrete idea about it, but I have interest to explore the data. Yeah. In touch a little bit on the sequence data.
Split your data.
Yeah, tomorrow I'm pretty sure there will be sequences because the big difference between classifying and sequence is in a sequence you want to have some memory. You don't want to forget what you just saw.
Yeah,
You just want to
but the relation between the this and the
Yeah.
the number
If you want.
and here there is no memory, there is nothing.
Okay, that's very well.
Okay, I see. And how can we find the suitable method for specific types of data?
I think just on one of the pages, just before you clicked on classify, there was a data set index. So here insert.
Yeah.
It seems like
Just always there. So yeah.
first of all, like it was originally externalized, but it's supposed to be trained.
Yeah, it should be true.
Oh, so it didn't actually didn't run.
So you might, it said,
Well, it's probably the difference.
oh yeah, so it said that.
Yeah.
Right.
At some point in your page, you had to click on classifier, and there are many different types of.
This is just the homepage. That's the homepage.
Oh yeah, so these are different types.
Basically.
Yeah, maybe here you have the different types of models.
Press backspace, you have an extra. You have an extra period.
Yeah.
Makes sense.
It depends on the algorithm. They have different,
Because we need to import the SQLs, should be able to. We need to import the SQLs, right? We don't have the SQL.
Okay, that's a good question. Where can you find a resource that will tell you? I will ask Suzana.
you change CLF to classifier. So this doesn't need it. It's actually wrong. There you go.
So the best part.
Yeah, what's the variable name? Okay.
Things like you did.
What is the next one? All right. Actually, I think people are still.
Oh god.
Sorry. But you can just jump to the lobby.
Maybe there is no special famous resource that can tell you that, but actual books.
Books.
Yeah, probably.
I'm gonna go through the cross-validation example. So again, the start is the same, but now what I want to do is rather than have a fixed train test split, I want to actually break the data set up into many different folds. So like in the slides, I have the data set, I want to say split it 5 ways, and then one of these is going to be the test set one time, and then one of these is going to be the test set the next time, and one of these is going to be the test set the next time, and so on. And that will basically help me get better use of my data, so I won't be throwing away data in evaluating my model. So I'm using this stratified shuffle split function from the scikit-learn stuff. This one is in the model selection module. And what this does is basically it shuffles the data and it tries to make those splits so that they all contain an equal number of the different classes. So that way I don't have the fluctuations in the frequency of the 2 different kinds of flower from batch to batch. So in initialize that thing, and I say I want 30% of the data in each of the tests. And then I get n splits on the data. And I need to input the data because it has to look at the labels and actually know how to break it down. And then what I'm going to do is I have this iterator. And what this is doing is when I call this split.split, it's a generator that gives me different cuts of the data. So every time this for loop iterates, I get a new train index and test index. And those are giving me different ways to divide up my data. I can split that into training and test sets. I can make my classifier, fit my classifier, do the prediction, get an accuracy, and then add it to a list. And at the end, I can look at the statistics of the list to understand how my model is doing. So before we just got one number, that's 96%. And this is actually going to say like 96% plus or minus 2%. So it actually gives me the ability to see some sense of how different the results could be if I cut my data differently. This isn't going to work because I didn't actually run the code. Let me actually run the code. Right, so now I see some of these splits I get 100% test accuracy. That would be great. Some of these splits I get a 93%, and on average it's about 97% plus or minus a little tiny bit. So this is very, very similar to the previous example, but now instead of just having one train test split, I'm letting scikit-learn give me many, many splits and averaging. And then in the hyperparameter search example, then we use that to actually figure out the values of these inputs to this SPC module. So I don't know, is that pretty straightforward? Should I just keep going? Okay.
I think so.
So then in the hyperparameter search example, let's get another model because SPC is too good. We need something really terrible. Let's do ridge regression again, right? That was really bad. Yes. Well, I didn't really also visualize it. I really don't want analysis. All right, ridge classifier. So again, in the hyperparameter search, it's the same, except now I'm going to be sweeping these parameters and looking at it. I realized I said all of this like 20 minutes ago. Sorry about repeating. And the ridge classifier, I think, also has the C parameter. It's the same C parameter as the support vector machine. It's essentially a regularization. So it makes the model not want to use very complicated shapes. No, it's not what's C. It's called it's alpha. Sorry. Okay, so we can definitely make the thing fall off a cliff. But basically, it's saying this parameter doesn't really matter for this data set. It's doing about the same no matter where it is. I might even be able to get error bars on this if we want. I can do STP scores and this. And then we can do fill between is a nice way of visualizing to make these numpy arrays. Right. So basically, it doesn't really matter what we do. We can do badly, but we can't really do better with ridge regression. Whereas the support vector classifier actually did have a peak. I suppose you might say maybe if I squint really hard, there is some peak around alpha is like 3 or something. So that's an example of how you can do this hyperparameter search for a single dimension. And if you want the multi-dimensional one, it gets very complicated, but we can look at the automatic null selection. And here I'm just going to throw everything at this problem. I'm not going to hold and do individual ones on their own. So I just load in a a bunch of different classifiers. We can add more if you like. Yeah, I'll run anyway. And here what I'm doing is I'm just defining a list of every model that I'm interested in. So in this list, I've got the name that I want to call it by so I know what I got. I have the actual scikit-learn module, not with parentheses, right? I'm not actually making an instance. That would be an instance. This is just the class. And then I've got this dictionary. And in the dictionary, I have everything that I want to try to vary. So it turns out that logistic regression, I can vary this penalty. I can vary the C value. Ridge classifier, I've got that alpha thing. Linear SVC, I've got the C value. Decision trees, there's criterion, max depth, min sample split, max features. All of these I just pull from the scikit-learn documentation. And then the values are generally things that you do have to have a little bit of experience with it to know what kind of values are reasonable, but you can essentially try based on what they say that these things are. Extra trees, gradient boosting, kernel SVC, naive Bayes, the works. And this is going to tell the thing what to search. It's going to basically say, here are all the different things I want to vary, try to find the best out of the entire list. Then I'm just going to define a function that basically does this for me and gets the cross-validation best hyperparameters for one model that I pass it. So I'm getting the classifier out of this this tuple that is associated with my array. So the first entry is the name, the second entry is the classifier, and the third entry is the parameters that vary. So I'm getting the classifier and the parameters that vary. And then I use this randomized search CV function that scikit-learn provides. If you pass it the classifiers, the parameters you want to vary, and then the number of iterations and how many splits, it will do all the splitting and everything internally, so you don't have to worry about that. Fit it to the data, and then you can literally just read off the best score from inside the module. So it creates this best score underscore thing. You can get the best parameters, the best estimator, etc. So I'm just defining that function. This will plot stuff, but we don't have to worry about it right now. So now the Iris dataset, same loader as before. And I still want to do a train test split because at the end I'm going to want to test on something independent of the whole cross-validation procedure, so I'll do that. Oops, run something here. Try that. You might have to change that line. So we run that, fine. I'm going to just do some pre-processing of the data to normalize it. It doesn't really matter for this problem too much, but now when I run this, it's just going to spit out for every algorithm the accuracy it can get. Some of these take longer than others. Yeah, that's a good question. I don't think I've ever seen it be good. That's a good question. They have the different kinds of linear model use both different ways of solving to find a solution. They use different regularizations. So like logistic regression says, I'm going to have a sigmoid kind of function. I want the probability to be according to the sigmoid. The SVC stuff is doing a linear problem that has this extra term that says that the coefficients of the linear model should be small. Ridge regression, I think, is also doing that, but the loss function it uses is different. Although SVC also has a ridge-based loss function, so that's a little weird. I don't know what's so special about the implementation of the ridge classifier that it's so terrible. Decision trees basically try to split the data, so they say like, let's say my data looks like I don't know this. Then it looks on the x-axis or the y-axis and it tries to put a cut that maximally separates the data. So it's like if I cut here, I could do a bit better if I cut here. If I cut here, I could do a bit better if I cut here. So let's cut here first. And then let's cut and I guess no cut because that's pure, right? So that would be an example of a decision tree. And the random forest generates hundreds and hundreds of these randomly with different choices of features and then averages them all together. And gradient boosting we haven't gotten there yet, but the gradient boosting classifier is on top of the random forest. You then like when you average them all together, you do so in this kind of iterative way that has a behavior like a learning rate. So you're actually, rather than classifying the data with each new tree, you're classifying kind of the misclassified points, and then you refine them all over and over. And that's a bit better than the random forest.
So the one you just shown that decision tree, that's like how I would look to do it myself.
Yeah.
By eye.
Yeah.
So could you explain very briefly how CDC is it?
Yes, you see?
Excellent, thank you.
I'll try. I said I wasn't going to do this. Well, I guess I could. All right, so let's say my data looks like this. There's this idea when people are thinking about generalization that what you really want, you don't want like the classification that optimizes the loss function. You want to find the line such that if I look at the data projected along this line, this margin between the two data surfaces, right? So I can kind of think that this line is actually like a no man's land where nothing occurs in here that is of either class. And what I would want to do is ideally make this as wide as possible, and that should give me the best generalization. So that's, I think, called the maximal separating hyperplane or something like that. And it turns out that finding this corresponds to linear regression, but with some fancy regularization term. And the reason, if these data are completely separated, okay, fine, right? Then I can find this. But let's say I had a red point there, what do I do? So if I soften this problem, so I want to find sort of like the widest gap on average or something like that, then I'm in the end solving the linear regression problem with this extra term that says like try to make sure that things that are mismatched are kind of minimized. And they define that somewhere in the psychedelic documentation exactly what that function is. But this is kind of the core idea. That's the linear version. Now the nonlinear version I can't really explain very easily because what it does is it says, okay, well, the distance here to the separating hyperplane, here it's distance in Euclidean space where everything is linear. But what if I just had some arbitrary way of getting distances between things and I didn't actually know what the space looked like at all? And there's something called the kernel trick where you can actually essentially have an infinite basis set of functions, but such that the distance matrix can still be calculated. So in that case, you end up having the distances between all these points, or you have a way of getting the dot products between all of these points. And then you're doing this kind of maximum margin thing in that sort of implicit space. And that is a trick that lets you essentially have an infinite basis set, but solve it with a finite number of coefficients. And the whole support vector is that the geometry of this is defined by a small number of data points that support the structure of the solution, so that the rest of the data is basically irrelevant. And that is responsible for why like linear regression scales quite well, but if you use SVC above 60,000 points, you get in trouble. Because it has some weird nonlinearities in how it scales with data. I don't know if that was helpful.
That was helpful, thank you.
Okay. All right, so yeah. So then you basically, after you run this thing, you get all of the different cross-validated accuracies and you can pick one. Which I guess in this case is a tie between logistic regression, linear SVC, and kernel SVC. Which again, Iris is too easy, so everything's the same. We can also see how these compare with the test scores, right? Because this is from cross-validation, but we have a held-out test set. So we can use that to see whether our cross-validation is working. And to that, we just plot them against each other. And well, if there were more differences in the data set, this would be more interesting, but basically everything is scoring the same. So there's not much to say, except ridge regression is terrible. And then you can actually plot the decision surfaces. So this is kind of like how these different algorithms are classifying it. And the ridge classifier is in fact pretty terrible. I don't know what it's doing. This one.
Oops.
Yeah, it's really awful. But the rest are pretty reasonable. Keep in mind also this is like a four-dimensional space and we're only seeing a cut. So this is not the whole story, but it's something.
Wait, can you plot a different dimension to see if the ridge classifier is.
Is better in those dimensions.
Yeah.
Well, okay.
It's a bit less bad, no?
You're being very generous.
It's less than-
Yeah. But you can kind of see the character of some of these algorithms, like the random forests and the decision trees. They all have a tendency to have axis-aligned decision boundaries. The SVCs are more kind of rotationally invariant decision boundaries. Basically, this SVC is using Gaussian basis functions. So it's just like sticking Gaussians everywhere in the plane randomly. Or I think a Gaussian around every data point is how it works. No, this is not the best axis to see what's going on. Let's do 0, 1. 2, 3 was pretty good, but let's see what we have here. Oh, okay. That's exciting. All right, so that's just not a good cut. Let's do 0, 4 or 0, 3. Yeah, because I have to fill in the missing values with zeros or with the average of the data. So sometimes that plane is going through a weird space. But yeah, here's another cut. You can kind of see linear ones have linear boundaries. The decision tree has very flat boundaries. Actually, everything has really flat boundaries in this space. Okay. And you can do the same thing with other data sets, and it's literally just drop in. So all I did is I changed load iris to load line, and then we can do the line data set. Running the same code as before.
Well, ridge is
wow,
going very
Ridge
good.
is doing well.
You found the one data set that's.
Yeah. But it's often like this, right? I wouldn't have been able to look at the line data set and say, yeah, ridge classification, this is obviously what we should use. Or iris, obviously we shouldn't use ridge classification. So and this is the kind of surface. This time I guess it doesn't look like ridge is doing very well, but similarly, there's a breast cancer data set. There's a bit, that's a harder data set. We actually have some scatter when we do it, but again, you can see the cross-validation and the test set are kind of correlated, so we have an idea of how much we can trust the cross-validation. And you can basically drop in any kind of classification data set to this workflow. Yeah.
So Nicholas, if you're not sure which classifier to use, it's kind of like, just throw everything and see which one gives the best.
Yes.
Like, prediction is the way to go.
Yeah. Yeah, that's the message I want to give, is that if you actually had to study each of these and read 5 papers to understand each of these in detail, it would be really hard to get anything done, because actually a lot of these are very idiosyncratic to the data. But by having a lot of them, you have access to a lot of things, and one of them might work. So all you need is a way to check. And as long as you can trust the way you're checking, you can just go ahead and safely use black box algorithms.
Is there like a payoff when you have like too much data to parse? Then you probably have to reduce the data set to actually get all the results out in the given time frame.
These are pretty fast. Like, of course, we're using 500 data point data sets at the biggest, and it still only takes a couple minutes. If we got above, say, 30,000 data points, I would start worrying about that.
Yeah, maybe people don't get a very good idea of the timescales that this kind of stuff can reach. Now we do it in a few seconds, but it can take days, weeks.
But this kind of thing almost never actually takes that long.
I mean, maybe not that.
Classic
Yeah.
machine learning is really, really fast. The exceptions are if you have SVC above 60,000 data points, it starts to get slow very fast, because it's cubic in the number of data. So it's as bad as doing like sequence alignments. And XGBoost can be a bit intensive if you make it really big. But other than that, these things are almost insane. I mean, basically, like in less than a minute, we're running maybe 500 different classification processes on this data set to get these numbers. And that's on a couple hundred data points. So especially if you had a cluster or something doing it for you. Now, when we train a neural network, it will be the complete other issue, right? It will be like, okay, let's come back in 30 minutes. Maybe not quite so bad because the GPUs are pretty good. But, all of this is being done on CPU, by the way. So you don't need to do this kind of machine and it won't necessarily help. Most of this code doesn't actually have GPU versions, I think.
Wow, you're so precise with time. It's impressive.
I'm not in control of the time. This is like when people are tired of being here, right? Yeah. Sorry. We can, but it's a totally different thing. Maybe it's a good idea for us to get some of this stuff out of the way.
Which one?
The triplet network. The embedding.
But you will talk about it tomorrow,
Tomorrow,
right?
yeah.
So.
But the one thing is, if people can download the data set and make sure that they put it on their drive tonight, that might speed things up.
Okay. Okay.
So, where is it?
But we're gonna load the data set tomorrow.
It's a different data set.
Oh, it's a different data set?
It's a different data set. That's what I don't know. Where is it? So if you, no, that's the this one. Okay. That's not a thing. It's a good thing we checked because I didn't upload the data. There was an error. Oh, okay. Thank you, Elizabeth. You just saved us some problems tomorrow. So I didn't upload the data for tomorrow. Yeah, there was an error. Don't push some. File size limit is 100 megs, so we can't go get help.
Well, drive.
You can push it. No, not terminal?
Yeah, it says this file is 180 megs. The CC helps file size limit 100 megs.
Store it somewhere and just do like download link.
Yeah.
Is it? Did you create that data or is it
Yes,
somewhere?
I did.
Okay.
Yeah, I just went to Google Maps and took screenshots.
So would it be worth uploading on OSF or Figshare or that kind of stuff?
I'm putting it in that document you gave me.
Okay.
This is just a share link to my Google Drive. So I'm sorry that the URL is annoying. I guess hopefully you can access the documents and just copy paste it. So yeah, if you go there, it's going to be a directory of images, and if you can make a copy of that whole directory on your Google Drive.
So there is option for that, and I will probably send
And
it.
then also upload a zip file, but then it would be like download the zip file, upload the zip file, unzip the zip file.
No, I think this will be fine.
180 megs. Yeah. And yeah, so this is the thing for tomorrow at the very end. We're going to be doing some neural network stuff that makes embeddings, that converts images like this into Turing maps like that. So that's, I guess, a teaser for. And you get embeddings like this that put like grass and sand and mountains and so on in different regions of space. So.
How did you just go to Google Map and type name of places that you?
No, I zoomed out, I looked at different terrain types, and I zoomed in. It's interesting. Snap.
Okay.
I think I did it in 2 hours after we were talking over Gmail about whether.
Yeah, I saw you were so fast, right?
I don't want to try to live code this.
Yeah, it's too much.
So probably after Suzana's section on neural networks, this code will hopefully make more sense to people. But if you want to get a preview now, this is what it's going to be, what the final thing is going to be about.
So tomorrow we will really learn from.
Okay. I'm hoping that will help.
Learn from coding.
I'm not sure how to actually explain this code like verbally, so
Yeah.
this might just be a bit tricky to get through, but we can try.
That's why I was thinking it's
I just want to get the idea, to get the idea out that this kind of method exists. So this is a way to embed data. It's like PCA, but all you need is a sense of similarity. And it's a different kind of tool than what we've been talking about. So there's not, like this color purple doesn't mean anything scientifically. You can't write a paper saying, oh yeah, this area is purple. Well, I guess you could write it, but it probably won't get past peer review. Maybe A-like. Yeah, you're right. They hate the black box machine learning.
And also it's just not interesting. This is purple.
Well, the purple, it seems to understand that this terrain is flat and this is mountainous.
Mm-hmm.
Okay, I'm not gonna get this name like. They actually use this for face recognition, and this same method was developed for saying like these two views of someone's face are more similar than this view of someone else's face, and it's very, very good for that. Basically, I think it's something like for a false positive rate of 1 in 1,000, it has like a 99% true positive rate, or something, or 99.9% true positive rate, or something like that. So this is it's also a useful method. It's not just a toy, but it is also a toy.
I guess.
So can I just for tomorrow we'll be writing a lot of code. We'll be mainly writing code tomorrow. And for our section, it's important so first of all, Colab seems to work. And the second thing is we'll be accessing the Kaggle API. So it would be great if you want to follow along with the code, if you want to write code, to just create a Kaggle account. And we'll show you how to access the API, how to download data sets, and how to work with data sets. This could be useful also in the future if you want to experiment with other data sets, but you don't have to. If you just want to observe and to look at the code, it's totally fine. But if you want to write code, it would be good to have a Kaggle
account.
Kaggle account.
I know the credentials are still in it on GitHub.
I think they've been removed.
This morning I was checking it. This afternoon.
You removed it yesterday.
You removed it from one of them, but not the other.
Oh, what?
Yeah, you better fix it.
Yeah, because you're gonna need your username and the key to download it. And not use Dimitris.
Not use Dimitris.